Hey, welcome back everyone to your favorite calculus class. Good to see you. We've got the logarithm defined as an integral. We're actually just jumping into this section only to finish off this content for our exam. The first bunch of slides here, just kind of reviewing a bunch of our rules and our pre-calculus as we get back into taking derivatives and integrals of our transcendental functions. Okay, so if you remember the natural log of b times x is the ln of b plus the ln of x, right? We've got our product rule there, or there it is with the logarithm. The natural log of b minus the natural log of x, same thing as ln of b over x. This is just an application of the uh, quotient rule there, because you got the ln of 1 over x, same as the ln of 1 minus the ln of x. We know that ln of 1 is 0, so negative ln of x there. And of course, our power rule on that, so ln of x to the r is the same as r times ln of x. These are unique to logarithms. If you remember, e to the x, its inverse is log base e of x, which we called the natural log of x, right? Log base e. So they undo each other because since they're inverses, inverses will, quote, undo each other, right? So if you do a composite function with those, e to the ln of x is x, or ln of e to the x is x. This one's just showing you, this is just an application of the power rule. If you rewrite this x ln of a as ln of a to the x, right? If you just apply that power rule, e and la and e and the natural log undo each other, right? So these undo each other, and you're just left with a to the x. So a to the x equals a to the x. And here it is with your log bases as well, right? So again, they're inverses, so they undo each other. Here's your laws of exponents, right? Like e to the second times e to the third is e to the fifth, e power of a power. There's where you multiply and so on. And again, inverses, right? Here we've got log base 2 of x. Its inverse is 2 to the x. They're reflective about the line y equals x because they're inverses there. Here's the natural log of x and then e to the x on in the yellow there. All right, so just a reminder, we remember that the derivative of the natural log of x is 1 over x, right? Or there it is with the absolute value as well. The integral of 1 over x is the natural log of the absolute value of x plus a constant there. Here's just another definition of the natural log. So if you think about your second fundamental theorem of calculus, if you were to take the derivative of this and the derivative over here, right? So the derivative of the natural log is 1 over x, and then the derivative will undo this. And if you remember, you're taking this derivative on the integral, and according to that second fundamental theorem of calculus, this will just go in for x, and then you take the derivative of x, which is just 1. So yeah, 1 over x equals 1 over x. This is just another definition of your natural log. The natural log of x is the same as the area under the curve for the function 1 over t dt from 1 to x. The derivative, we usually wrote it with a to the x. Derivative of a to the x is ln of a times a to the x. The integral of a to the x is 1 over ln of a times a to the x plus our constant. Of course, e to the u is just an application of e to the x. So if we're taking the derivative, e to the x, we got the ln of e times e to the x. Well, the ln of e is just 1, right? ln of e to the 1, they undo each other. So e to the x. The integral of e to the x is 1 over ln of e times e to the x. Again, just an application of the rule we just followed. ln of e is just 1, so you got 1 over this is 1 right here. So we just got x plus our constant. And then how about log base a of u? So the derivative, let me do it with x, log base a of x. So if you remember, you can change the base on these. This is the same as ln of x over ln of a. And ln of a is a constant. All right, so here's another way to say it. So if you're going to take the derivative on this, you've got the constant that stays out front, right? A, because 1 over ln of a, again, a will be a number there, so you get your base. And then you get the derivative of ln of x, which is just 1 over x. So this is just 1 over ln of a times 1 over x. That's your derivative of the log base a of x. Right? All right, so let's solve this differential equation now. Let's actually do some new examples here. Let's take this dx to the other side. So we've got dy equals 1 over x ln of x dx. And let's integrate now. So we're integrating 1 with respect to y, dy there. So we got y over here. Now I'm looking at this. I got 1 over x ln of x. So how can we get this? I'm thinking to myself, well, gosh, I know that the integral of 1 over x dx is the natural log of x, right? Like I can do that. Can we get it in that form? Well, you're going to have to use u substitution to do that. So what you're going to do is you're going to let u be the ln of x. So this part right here, right? So I know du dx is 1 over x. And then, of course, I take the dx to the other side. Now let's look at this. So I've got 1 over x. I've also got this ln of x dx. So here, 1 over x dx, there's my du. And then there's my u, so I got 1 over u. And now we can run it. We can run the integral, right? This is the same as right here. We've got 1 over u. We know the integral of 1 over u du is the natural log of the absolute value of u plus a constant. And now we just throw u in. What was u? U was the ln of x. So it's the ln of the absolute value of the natural log of x plus a constant. Let's do some more. How about the tangent? I think to myself, well, what if I didn't know the integral of the tangent? What about if I thought about that like the sine over the cosine? I know sine over cosine is a tangent. And then what if I let u be, my denominator there, that cosine of x? So du dx would be negative sine x dx. Now I have sine x dx, I don't have negative sine x dx. So I'm going to go ahead and add in the negative, so I have negative sine x dx, I got to offset it on the outside. So there's my du part, right? And then my u is on the bottom, that cosine of x is on the bottom. So this becomes, negative stays there, 1 over cosine again. Cosine is u, and then all this stuff is du. I say, oh, the integral of 1 over u du, natural log of the absolute value of u. Put that u back in, and there we are. Negative natural log cosine x plus a constant. Let's keep going here. This one's a little bit tricky. You're thinking about how can I get it in this form, where I have something that I can integrate. Natural log, right? So look at that log base 2 of x. Here's where that pre-calc comes into play. If we change the base on that, so I rewrite log base 2 of x. Log base 2 of x is the same as the natural log of x over the natural log of 2, if you remember from your pre-calc. So I'm going to change that base. And the reason I change that is I'm looking at this ln of 2 over ln of 2. And I can cancel those. So this becomes the integral of the ln of x over x dx from an x being 1 to x being 4. And now, what am I going to do here? Well, let's let u be ln of x. Because I know the derivative is 1 over x. So I've got ln of x dx, or I'm sorry, I got u. There's my u. Oops. Here, let me rewrite this. ln of x over x dx from 1 to 4. Okay, u is my ln of x. Here's my u. And then I've got 1, here's a 1 on top, over x dx. There's my du, right? There's my du, 1 over x dx. And I'm integrating this from x being 1 to x being 4. So I run the integral of u du, which is u squared over 2 from, remember, this is x being 1 to x being 4. So I either got to change the x's to u's, or I just got to substitute the u in. I'll just go ahead and substitute the u in and keep this in terms of x, from 1 to 4. So now the 4 goes in, ln of 4 squared over 2 minus, now the 1 goes in, ln of 1, which is squared all over 2. So I got the ln of 4 squared over 2 minus, we know the ln of 1 is 0. 0 squared over 2. And then from here, it's just a matter of how far do you want to take this thing. The ln of 4, so it's gone. That's ln of 2 squared. So I could use the power rule on this and write this as 2 ln of 2 over 2. Now remember, this numerator's being squared. So the 2 is squared and the ln of 2 is squared. So the 2 squared and the ln of 2 is squared. Right? This is power of a product there. So I got 4 ln of 2 squared over 2. Well, 4 over 2 is 2. So 2 ln of 2 quantity squared. And there's our solution on that thing. All right, let's do another one. I just love, I gotta get back to my blue here. Let's say dy dt, we've got e to the t sine of e to the t minus 2. We're solving this initial value problem. So they're giving us the fact that the y of the natural log of 2 equals 0. So that when we go ahead and solve this thing, you take your dt to both sides here. And we go ahead and we integrate this. Now we're stuck looking at this, thinking, well, how am I going to do this? Well, I got to use the old u substitution. So let's go ahead and let u be e to the, oops, that's a t right there, e to the t minus 2. And so du dt, so I'm taking the derivative of that e to the t. Remember, derivative of e to the t minus 2, if you're taking that derivative, this is the ln of e to the t minus derivative constant is 0. So ln of e is just a 1, right? This is just 1, so it just ends up being e to the t. And then you take the dt over. Right? So let's see here. We've got e to the t dt. There's our du. And then we got sine of u right there. So this becomes sine u, and then du, because du is e to the t dt. And I say, oh, I can integrate that. Bring that over here. The integral of the sine is negative cosine. So negative cosine of u plus a constant. Let's throw our u back in. So negative cosine, our u is e to the t minus 2. Now I would stop here, but they gave us an initial value here. They told us that y of the natural log of 2. So if I plug in ln of 2 for uh, t, y of the ln of 2 is equal to 0. Now, e and the natural log undo each other. We know the cosine of 0 is 1. Add 1 to both sides. It looks like our constant's 1, so now we know our constant, don't we? So I can take this and say, oh, that means y is negative cosine e to the t minus 2 plus the constant, so plus 1. And then we can solve that initial value problem. Well, thanks for listening. If that helps. See you guys soon.